Buckminsterfullerene is a spherical fullerene molecule with the formula C60. It has a cage-like fused ring structure which resembles a football, made of 20 hexagons and 12 pentagons, with a carbon atom at each vertex of each polygon and a bond along each polygon edge. It was first generated in 1985 by Harold Kroto, James R. Heath, Sean O'Brien, Robert Curl, and Richard Smalley at Rice University. Kroto, Curl and Smalley were awarded the 1996 Nobel Prize in Chemistry for their roles in the discovery of Buckminsterfullerene and the related class of molecules, the fullerenes. The name is a reference to Buckminster Fuller, as a C60 resembles his trademark geodesic domes. Buckminsterfullerene is the most common naturally occurring fullerene molecule, as it can be found in small quantities in soot. Solid and gaseous forms of the molecule have been detected in deep space. Buckminsterfullerene is one of the largest objects to have been shown to exhibit wave-particle duality, as stated in the theory every object exhibits this behavior. Its discovery led to the exploration of a new field of chemistry, involving the study of fullerenes. Etymology: Buckminsterfullerene derives from the name of the noted futurist and inventor Buckminster Fuller. One of his designs of a geodesic dome structure bears great resemblance to C60. As a result, the discoverers of the allotrope named the newfound molecule after him. The general public, however, sometimes refers to Buckminsterfullerene, and even Mr. Fuller's dome structure, as bucky-balls. History: the structure associated with fullerenes was described by Leonardo da Vinci. Albrecht Dürer also reproduced a similar icosahedron containing 12 pentagonal and 20 hexagonal faces, but there are no clear documentations of this discovery. Theoretical predictions of bucky-ball molecules appeared in the late 1960s, early 1970s, but they went largely unnoticed. In the early 1970s, the chemistry of unsaturated carbon configurations was studied by a group at the University of Sussex, led by Harry Kroto and David Walton. In the 1980s, a technique was developed by Richard Smalley and Bob Curl at Rice University, Texas, to isolate these substances. They used laser vaporization of a suitable target to produce clusters of atoms. Kroto realized that by using a graphite target, any carbon chains formed could be studied. Another interesting fact is that, at the same time, astrophysicists were working along with spectroscopists to study infrared emissions from giant red carbon stars. Smalley and team were able to use a laser vaporization technique to create carbon clusters which could potentially emit infrared at the same wavelength as had been emitted by the red carbon star. Hence, the inspiration came to Smalley and team to use the laser technique on graphite to create the first fullerene molecule. C60 was discovered in 1985 by Robert Curl, Harold Kroto and Richard Smalley. Using laser evaporation of graphite, they found CN clusters, of which the most common were C60 and C70. A solid rotating graphite disc was used as the surface from which carbon was vaporized using a laser beam, creating hot plasma that was then passed through a stream of high-density helium gas. The carbon species were subsequently cooled and ionized, resulting in the formation of clusters. Clusters ranged in molecular masses, but Kroto and Smalley found predominance in a C60 cluster that could be enhanced further by letting the plasma react longer. 3.6. They also discovered that the C60 molecule formed a cage-like structure, a regular truncated icosahedron. For this discovery they were awarded the 1996 Nobel Prize in Chemistry. The discovery of bucky-balls was surprising, as the scientists aimed the experiment at producing carbon plasmas to replicate and characterize unidentified interstellar matter. Mass spectrometry analysis of the product indicated the formation of spheroidal carbon molecules. The experimental evidence, a strong peak at 720 atomic mass units, indicated that a carbon molecule with 60 carbon atoms was forming. but provided no structural information. The research group concluded after reactivity experiments that the most likely structure was a spheroidal molecule. The idea was quickly rationalized as the basis of an icosahedral symmetry closed-cage structure. Kroto mentioned geodesic dome structures of the noted futurist and inventor Buckminsterfullerene as influences in the naming of this particular substance as Buckminsterfullerene. Further developments. The versatility of fullerene molecules has led to a large amount of research exploring their properties. One interesting property is the relatively large volume of the internal space of the molecule. Atoms of different elements may be placed inside the molecular cage formed by the carbon atoms. Beam experiments conducted between 1985 and 1990 provided more evidence for the stability of C60 while supporting the closed-cage structural theory and predicting some of the bulk properties such a molecule would have. Around this time, intense theoretical group theory activity also predicted that C60 should have only 4 IR active vibrational bands, on account of its icosahedral symmetry. In 1989, physicists Wolfgang Kretschmer and Donald R. Huffman observed unusual optical absorptions in thin carbon films produced by arc-process graphite rods. Among other features, the IR spectra showed 4 discrete bands in close agreement to those proposed for C60. A paper published by the group in 1990 followed on from their thin film experiments and detailed the extraction of a benzene-soluble material from the arc-processed graphite. This extract had crystal and X-ray analysis consistent with arrays of spherical C60 molecules, approximately 0.7 nanometers in diameter. In 2012, a toxicity study by Tariq Bhatti and Fathi Morsa from the University of Paris showed that C60 dissolved in olive oil was not toxic to rodents. In a video interview with Professor Fathi Morsa regarding the study, further information was provided regarding the toxicity study and the method of action whereby the lifespan of the rodents was increased by 90% relative to controls when the animals were dosed with C60 olive oil. Synthesis. In 1990, Kretschmer and D. R. Huffman developed a simple and efficient method of producing fullerenes in gram and even kilogram amounts, which has boosted the fullerene research. In this technique, carbon soot is produced from 2 high-purity graphite electrodes by igniting an arc discharge between them in an inert atmosphere. Alternatively, soot is produced by laser ablation of graphite or pyrolysis of aromatic hydrocarbons. Fullerenes are extracted from the soot using a multi-step procedure. First, the soot is dissolved in appropriate organic solvents. This step yields a solution containing up to 75% of C60, as well as other fullerenes. These fractions are separated using chromatography. Generally, the fullerenes are dissolved in hydrocarbon or halogenated hydrocarbon and separated using alumina columns. Properties. Molecule. The structure of a Buckminsterfullerene is a truncated icosahedron with 60 vertices and 32 faces with a carbon atom at the vertices of each polygon and a bond along each polygon edge. The van der Waals diameter of a C60 molecule is about 1.01 nanometers. The nucleus-to-nucleus diameter of a C60 molecule is about 0.71 nanometers. The C60 molecule has 2 bond lengths. The 6-to-6 ring bonds can be considered double bonds, and are shorter than the 6-to-5 bonds. Its average bond length is 0.14 nanometers. Each carbon atom in the structure is bonded covalently with 3 others. The C60 molecule is extremely stable, withstanding high temperatures and high pressures. The exposed surface of the structure can selectively react with other species while maintaining the spherical geometry. Atoms and small molecules can be trapped within the molecule without reacting. C60 undergoes 6 reversible, 1 electron reductions to C6-60, but oxidation is irreversible. The first reduction needs ~1.0 V, showing that C60 is a moderately effective electron acceptor. C60 tends to avoid having double bonds in the pentagonal rings, which makes electron delocalization poor, and results in C60 not being superaromatic. C60 behaves very much like an electron-deficient alkene and readily reacts with electron-rich species. A carbon atom in the C60 molecule can be substituted by a nitrogen or boron atom yielding a C59N or C59B respectively. Solution fullerenes are sparingly soluble in aromatic solvents such as toluene and carbon disulfide, but insoluble in water. Solutions of pure C60 have a deep purple color which leaves a brown residue upon evaporation. The reason for this color change is the relatively narrow energy width of the band of molecular levels responsible for green light absorption by individual C60 molecules. Thus, individual molecules transmit some blue and red light, resulting in a purple color. Upon drying, intermolecular interaction results in the overlap and broadening of the energy bands, thereby eliminating the blue light transmittance and causing the purple to brown color change. C60 crystallizes with some solvents in the lattice. For example, crystallization of C60 in benzene solution yields triclinic crystals with the formula C64C6H6. Like other solvates, this one readily releases benzene to give the usual FCC-C60. Millimeter-sized crystals of C60 and C70 can be grown from solution both for solvates and for pure fullerenes. Solid in solid Buckminsterfullerene, the molecules C60 stick together via the van der Waals forces in the FCC motif. At low temperatures the individual molecules are locked against rotation. Upon heating, they start rotating at about -20 degrees Celsius. This results in a first-order phase transition to a FCC structure in a small, yet abrupt increase in the lattice constant from 1.411 to 1.4154 nanometers. C60 solid is as soft as graphite, but when compressed to less than 70% of its volume it transforms into a superhard form of diamond. C60 films in solution have strong nonlinear optical properties. In particular, their optical absorption increases with light intensity. C60 forms a brownish solid with an optical absorption threshold at ~1.6 electron volts. It is an N-type semiconductor with a low activation energy of 0.1-0.3 electron volts. This conductivity is attributed to intrinsic or oxygen-related defects. FCC-C60 contains voids at its octahedral and tetrahedral sites which are sufficient large to accommodate impurity atoms. When alkali metals are doped into these voids, C60 converts from a semiconductor into a conductor or even superconductor. Band structure and superconductivity. In 1991, Haddon et al. Found that intercalation of alkali metal atoms in solid C60 leads to metallic behavior. In 1991, it was revealed that potassium-doped C60 becomes superconducting at 18 K. This was the highest transition temperature for a molecular superconductor. Since then, superconductivity has been reported in fullerene doped with various other alkali metals. It has been shown that the superconducting transition temperature in alkaline metal-doped fullerene increases with the unit cell volume 5. As cesium forms the largest alkali ion, cesium-doped fullerene is an important material in this family. Recently, superconductivity at 38 K has been reported in bulk Cs3C60, but only under applied pressure. The highest superconducting transition temperature of 33 K at ambient pressure is reported for Cs2RbC60. The increase of transition temperature with the unit cell volume had been believed to be evidence for the BCS mechanism of C60 solid. Superconductivity. because inter-C60 separation can be related to an increase in the density of states on the Fermi level. Therefore, there have been many efforts to increase the interfullerene separation, in particular, intercalating neutral molecules into the A3C60 lattice to increase the interfullerene spacing while the valence of C60 is kept unchanged. However, this ammoniation technique has revealed a new aspect of fullerene intercalation compounds: the Mott transition and the correlation between the orientation, orbital order of C60 molecules and the magnetic structure. The C60 molecules compose a solid of weakly bound molecules. The fullerenes are therefore molecular solids, in which the molecular properties still survive. The discrete levels of a free C60 molecule are only weakly broadened in a solid, which leads to a set of essentially non-overlapping bands with a narrow width of about 0.5 electron volts. But when the C60 solid is doped with metal atoms, the metal atoms give electrons to the T1U band or the upper threefold T1 gram band. This partial electron occupation of the band may lead to metallic behavior. However, A4C60 is an insulator, although the T1U band is only partially filled and it should be a metal according to band theory. This unpredicted behavior may be explained by the Jahn-Teller effect, where spontaneous deformations of high-symmetry molecules induce the splitting of degenerate levels to gain the electronic energy. The Jahn-Teller type electron-phonon interaction is strong enough in C60 solids to destroy the band picture for particular valence states. A narrow band or strongly correlated electronic system and degenerated ground states are important points to understand in explaining superconductivity in fullerene solids. When the inter-electron repulsion U is greater than the band width, an insulating localized electron ground state is produced in the simple Mott-Hubbard model. This explains the absence of superconductivity at ambient pressure in cesium-doped C60 solids. Electron correlation-driven localization of the T1U electrons exceeds the critical value, leading to the Mott insulator. The application of high pressure decreases the interfullerene spacing. Therefore, cesium-doped C60 solids turn to metallic and superconducting. A fully developed theory of C60 solids superconductivity is still lacking, but it has been widely accepted that strong electronic correlations in the Jahn-Teller electron-phonon coupling produce local electron pairings that show a high transition temperature close to the insulator metal transition.